Okay, then please start.
Yeah. So, oh, did my screen share still good? You can still see it? So thank you for the kind invitation to speak, and thank you for accommodating the schedule. I know it's not easy with the time difference between the US and Korea, so I really appreciate the chance to give this talk. I'm going to tell you about some recent work over the last year with some of my collaborators regarding neutrino self-interactions and some interesting phenomenology that results from having strong neutrino self-interactions, specifically resolving the long-standing Hubble tension and some interesting avenues for sterile neutrino dark matter. So to give a brief outline, I'll try to motivate the idea of neutrino self-interactions and what we know about their possibility. I'll talk about how self-interactions modify cosmological predictions and specifically the Hubble tension. And then I'll talk about the possibility of sterile neutrino dark matter and how self-interactions play a significant role for that. So to start, let me motivate what we know or don't know about neutrino self-interactions. The result will be that we don't know a ton, I guess. So we have not observed any self-interactions among neutrinos, but we have good reason to believe that they exist because of how neutrinos interact with the other standard model particles via the weak interactions. So we know that neutrinos interact via the Z boson, and so it's not too crazy to suggest that diagrams like this with 4 neutrinos exist. Like I said, we haven't observed this, but it should happen. And the associated strength of such self-interactions is set by the weak scale, G Fermi being about 10 to the minus 4 GeV to the minus 2, or 10 to the minus 10 MeV inverse squared. That's going to be kind of the scale of what we're comparing against. If we want to have any new interactions, if we want them to manifest themselves in any real meaningful way, we're going to need self-interactions that give an effective coupling that's larger than this interaction. So the simplest question you can ask is, what if there are new mediators beyond the standard model weak bosons that exist that are neutrinophilic? So the first approach that we took was to ask what this could look like for a scalar mediator, call it phi. And to give a concrete model, we say that phi couples to the neutrinos via this dimension 6 operator that looks kind of like the Weinberg operator plus the scalar phi interacting with the neutrinos. The reason we choose this interaction as opposed to some other possible ones is so that we don't generate large charge lepton interactions, because we know that there are strong constraints from charge leptons with light mediators. So after electroweak symmetry breaking, and if the Higgs acquires its VEV, you end up with a term in your Lagrangian that looks like this, where we define lowercase lambda as the Higgs VEV squared divided by the scale of new physics squared. And it talks to neutrinos, nu alpha, nu beta, phi. This specific model, phi carries lepton number, and we're assuming that the neutrinos are direct, but really none of the phenomenology depends too strongly on that assumption. You can get some interesting phenomenology if you say that phi carries lepton number, and you can look for these signals in neutrino experiments, but I'm not going to dwell on that too much. I will note that we assume that these couplings lambda, alpha, beta can be flavor dependent. So we'll look at all possible combinations of alpha and beta throughout. So depending on the mass of your new particle phi, you could have it being emitted in really any process that involves neutrinos, as long as the coupling is strong enough. Not only that, but since you have a particle that couples to a neutrino current, you can generate a 4 neutrino interaction similar to the diagram I showed above, with phi mediating the interaction. And if phi is lighter than the standard model weak bosons and lambda isn't too small, then you can generate pretty large self-interactions. So like I said, the coupling can be flavor dependent. So we want to ask, what do we know about the possible range of couplings or masses of phi to neutrinos? So let me talk about a few constraints on these types of interactions. So the dimension 6 operator that I wrote down, it generates two terms after electroweak symmetry breaking to leading order in the Higgs field H. There's the one that I showed that generates a new phi vertex, but there's one that's a dimension 5 operator that involves a physical Higgs field, where you have a 4-particle vertex between the Higgs, the phi, and the two neutrinos. So as long as phi is lighter than the Higgs, this will generate decays of this type, where a Higgs decays into two neutrinos and a phi instantly. So we can take this interaction and we can ask, what does this do to the standard model Higgs? If lambda is too big, then this will generate a large invisible width contribution to the Higgs boson. And the width of this process scales like this: lambda squared m Higgs cubed over 384 pi cubed v squared. So using what we currently know about the Higgs, its measured width, and its branching ratio into invisible final states, we can set an upper limit on all of the couplings of phi to neutrinos to be less than about 0.7 or 0.8. As you go above 10 GeV, this limit would soften because this decay would no longer be kinematically allowed for heavy enough phi. But since we're really interested in order GeV and below, this is really just a flat limit as a function of the phi mass. Now with the high Lumi LHC, this will improve by, I think the limit on the invisible branching fraction of the Higgs gets a factor of a few stronger, which pushes the sensitivity to lambda a factor of a few stronger as well. Next, I want to talk about the invisible decay of the Z boson. So one dominant decay channel of the standard model Z is to pairs of neutrinos. But if you can emit neutrinos, and if phi is lighter than your decaying particle, then you can have phi radiated off the final state as well. So to leading order in the phi mass relative to the Z mass, we can calculate this contribution to the invisible width of the Z. And this is how it scales. It scales like G Fermi, mz cubed lambda squared times a function of the masses divided by a numerical factor. And then this factor here, 1 plus delta alpha beta squared, comes from the fact that if we're considering identical flavor final state fermions, then these are identical final states. So we have to take a factor of 2 in this width for symmetry reasons. This comes from the assumption that phi carries lepton number. If phi does not carry lepton number, you would have a neutrino coming out here and an anti-neutrino here, and this factor of 2 wouldn't apply. So we can ask, what does the current constraint on the invisible width of the Z have to say about this? And we get these limits. This is showing the coupling to muon type neutrinos, just for simplicity. And the diagonal coupling, lambda mu mu, has the constraint with this solid line that's slightly weaker than the constraint with off diagonal lambda mu e or mu tau. But you see that as long as you're below a few GeV, this leads to a stronger limit than the Higgs decay. And it gives you an upper limit on the order of 0.3 for the coupling as a function of the phi mass. The next thing we want to consider is a wide variety of charged meson decays. This is where a lot of the flavor dependence comes into play. So if you have a charged meson that can decay into one of the standard model charged leptons and a corresponding anti-neutrino, you can emit phi, and depending on whether the flavor coupling is diagonal or not, you can emit a neutrino of flavor beta or alpha. So this is where flavor dependence comes in because of the different possible final state charge leptons in different meson decays. So the four that we consider for completeness are pion decay to E neutrino NFI, D decays to E neutrino NFI, and then kaon decays to E nu phi and mu nu phi. So this will have a lot of different mass dependence because of the charged lepton masses being relevant here. The thing I should mention is the way that we constrain this. If you had the decay process, for instance, pi to E nu phi, this would look like a pion decay to an electron and 3 neutrinos. It's no longer a two-body decay pi to E nu with a monoenergetic E coming out. So you could look for the 3 neutrino final state and consider upper limits on that kind of search as an upper limit on this type of process. So we calculate the branching ratio of the charged meson into this final state as a function of the phi mass and the charged lepton mass, etc., and the coupling. And this is what we get for limits on the couplings to electron flavor neutrinos. So for low masses, we see that the kaon decay limit dominates, mostly just because of the precision to which this decay has been measured. The pion decay limit is slightly weaker, but still competitive. We see that that limit dies off at lower phi mass because of the relatively low pi mass relative to the kaon mass. And then if we consider the D meson decay, we see that it's not as strong of a limit at low masses because this process hasn't been as well studied in the lab. But because the D is so much heavier than the K, we can rule out a little bit of parameter space using the D decay around 500 MeV or so in phi mass. So the story is at heavy masses, these heavy boson decay searches are relevant and give you a limit on the order of couplings of 0.1 to 1. At low masses for electron couplings, we have meson decays that limit this to order 10 to the minus 2. Similarly, we can do this process for muon flavored couplings, and we see that the kaon decay search dominates pretty much everywhere except for when the Z and Higgs decays take over at high masses. The D decay constraint is not relevant because it's beaten at all masses by any other process. So now let me talk about one final process for constraining the electron flavor couplings, and this is Neutrinoless double beta decay. So let me walk through this in order from left to right. On the left, we have a diagram that shows what we would refer to as standard Neutrinoless double beta decay, where there is some Majorana mass contribution for the light neutrinos that allows this diagram to occur, where we have 2 neutrons inside of nuclei to spontaneously convert into 2 protons and emit 2 electrons with nothing else in the final state. Now, experiments search for this process, hoping to determine whether neutrinos are Majorana or Dirac fermions. And the main background for this process is what I would call 2 neutrino double beta decay or neutrino full double beta decay. And this is where the 2 neutrons choose to convert at the same time. However, instead of the neutrinos tying themselves together via this Majorana mass, they are emitted in the final state. Now, because the initial state nucleus is mostly at rest, in the neutrinoless double beta decay search, you would look for the sum of these 2 electrons being a line in your spectrum. However, the 2 neutrino double beta decay, because the neutrinos are carrying away some of the energy, this process exhibits a spectrum of electron energies when you sum them. So you look for a bump on the top of a smooth background at the endpoint. Now, if phi carries lepton number like we have posited, and it couples to electron-flavored neutrinos, then it can be emitted in this type of process as long as phi's mass is less than the Q value of this transition. And the Q value of double beta decaying nuclei is on the order of several MeV. So now if phi is radiated and it carries away some energy and momentum in this process, then the two electrons that we could measure in this process would exhibit an energy spectrum similar to that of neutrino full double beta decay, not a line like neutrinoless double beta decay. So the emission of the new particle mimics the background of these double beta decay searches, and we can use that to constrain couplings to electron-flavored neutrinos. So this effectively puts a wall in your coupling versus mass space below a couple MeV from these neutrino full double beta decay constraints, if this is the coupling lambda EE. Now, as we'll see later, this only goes so low in coupling space, but it's a very powerful probe. Are there any questions on this constraint discussion before I move on to the next section of the talk? Okay, I'll move on. So now I will talk about neutrino self-interactions in cosmology and how these types of self-interactions can modify our standard cosmological predictions and lead to some interesting results. So let's go back to the idea that the only interactions among neutrinos are the weak interactions. And this is the only way that neutrinos couple to the standard model fermions as well. We can ask what is the rate of this process as a function of temperature. And we know that this scales like temperature to the 5th times G Fermi. We can compare this process's rate to that of the expansion rate of the universe to ask where are these interactions relevant, cosmologically speaking. And this is given by this black line where we're plotting the rate divided by Hubble, where if it's bigger than 1, this process is in equilibrium, and if it's less than 1, this process is becoming irrelevant. And we see that as temperature decreases, this rate is decreasing as well because it has a very strong T dependence. And this interaction starts to become irrelevant around the time during which nuclei are being formed during Big Bang nucleosynthesis. So
excuse me?
Yes.
Excuse me. The dimension of the gamma W is energy, right?
Yeah, I think I missed the power of
G
square.
Fermi. Okay.
Yeah.
G square. Okay. Thank you.
Thank you. I'll fix that. So it's very exciting that the standard model weak interactions are crossing this dashed line around the time of BBN. This means that BBN is a good probe for the standard model weak interactions and any possible BSM interactions. So I'll get to this SI nu, that stands for strongly interacting neutrinos, regime later, but this is just to say that if you add some new interaction that functions as the 4 fermion interaction with a similar G effective squared T to the 5th, these interactions can be very much relevant during BBN and possibly even freezing out around the time of the cosmic microwave background formation, which would mean that the CMB would be a powerful probe of such strong interactions where it's not really sensitive to the effects of the standard model weak interactions. Now, if these interactions are strong around the time of BBN or CMB, This means that even if the neutrinos have decoupled from the rest of the standard model particles, it means they will still remain in strong interactions with each other, and this will delay the temperature at which they begin to free stream. That can modify things like structure formation and the CMB power spectrum. So if these strong interactions exist, these interactions remain in equilibrium for much longer than predicted in standard cosmology. And the question is, is this good? Is this bad? Becomes a question of what the CMB power spectrum and associated probes measure. Not to put too fine a point on it, but this actually ends up helping a long-standing cosmological tension between two types of measurements of the expansion rate of the universe, which is known as the Hubble tension. And I'm a big fan of this figure from Wendy Freeman from last year that shows how measurements of the Hubble constant, h0, in units of kilometers per second per megaparsec, how measurements of different types have evolved over time to make this tension much more significant. So the blue data points and the band are measurements of the expansion rate using the Cepheid variable star method and high redshift supernovae to measure the local Hubble constant using these observations. And you can see that over the last couple of decades, these measurements have gotten about a factor of 2 more precise, and their central value hasn't shifted too much. They prefer a value of h0 around 72 kilometers per second per megaparsec. The other probe that I'll focus on is using the cosmic microwave background to understand the Hubble constant. Now, I'll mention that in terms of which one of these is a more direct measurement of the Hubble constant, it's really the expansion rate coming from Cepheids. The cosmic microwave background requires some orthogonal measurements to infer the value of the Hubble constant at early times. Now, these measurements have gotten more and more precise with the onset of the Planck satellite, and we see that not only have the error bars on that measurement shrunk over time, but they've also moved to preferring a lower value of the Hubble constant, around 67 kilometers per second per megaparsec. Now, the exciting thing is that other types of probes of the Hubble constant have become viable over the last 5 or so years. The one that's shown on this figure is using what's called the tip of the red giant branch, where astronomers look for the formation of red giant stars on Hertzsprung-Russell diagrams and use a characteristically known feature of how red giants form to pin down the distance to these galaxies. And so over the last 5 or so years, this approach has become more and more powerful to the point that independent of Cepheid measurements and CMB measurements, they can measure h0, and they get a relatively weaker error bar than the other 2 approaches. However, what's exciting is that they extract a value of h0 that's somewhere between the 2 of them. So what's going to happen in the next 10 or so years is unknown to everyone, but if these 3 types of probes continue shrinking error bars, who knows what this tension will have to say. Another way to look at this is just as one-dimensional measurements of h0 from a variety of different types. The CMB measurement I showed is here. The Cepheid variable star measurement that was black on the previous slide, or blue on the previous slide, is here. And the tip of the red giant branch is in the middle with a relatively larger error bar. There's also the approach of using strong gravitational lenses between here and a source and looking for time delays. That is getting more and more precise, as well as extractions from Big Bang nucleosynthesis and baryon acoustic oscillations. So it's very exciting that these things all are kind of all over the map. But the biggest tension is when you compare CMB to Cepheid variable stars measurement of h0, and you see that there's about a 4 sigma discrepancy between these 2. Now, again, I'll highlight that the Cepheid measurements of h0 are so to speak, local measurements of the expansion rate of the universe, whereas the CMB is an early time inference of the expansion rate. So there's a lot of ingredients that go into the CMB prediction that are not there for the Cepheids. So in early 2019, a group from Kreisch et al. Explored what would happen to the cosmic microwave background if you included strong neutrino self-interactions in your simulation of CMB. So what they did is they added an effective interaction between 4 neutrinos, where they just put a constant 4 Fermi interaction that they call G effective in their neutrino interaction. They assumed that this was flavor universal, and that it was a 4 Fermi interaction for all temperatures considered in their simulations. And to summarize what they found, I like this figure. The different data sets being used are the Planck power spectrum, the different components of it, a combination with lenses and BAO data, and then a combination that included a prior from the local measurements of the Hubble constant. And what you see in, let me look at this N effective versus H naught plane first. You see that once you include this power spectrum plus lensing and BAO, the data start to prefer relatively large values of the parameter N effective, the number of effective degrees of freedom in radiation at the time of CMB. But they also start to prefer a significantly larger value of the Hubble constant than standard cosmological extraction from the CMB does, around 68 or 65 or so. Of course, if you add in a prior from the Hubble constant, that will drive you up further. But the point is that the blue and red measurements are in fairly strong agreement with one another. Now, in order to get this high value of the Hubble constant to be preferred, you need fairly strong self-interactions. There are these kind of 2 blobs in which this solution works, the one at very high values of G effective that they call the strongly interacting neutrino solution, SI-nu, and then one that's an order of magnitude or so smaller in G effective that they call the moderately interacting neutrino, or MI-nu solution. So put in terms of values of G effective preferred, we can determine the preferred range of G effective that can resolve the Hubble tension. Now, I'll note that the resolution is much more powerful or viable in the SI-nu solution than it is in the MI-nu solution, but it's still very interesting to explore both of these possible scenarios. However, as I showed on the previous slide, these solutions require very large values of N effective. If you just do a standard cosmological calculation, N effective at the time of CMB should be a little bit over 3. So their simulations, however, require for this solution to work the number of effective degrees of freedom at CMB times to be closer to 4, so an extra degree of freedom in the early universe at CMB times, and the sum of the neutrino mass to be fairly large compared to the limits you get from standard cosmological calculations. Now I'll highlight that the ranges of G effective are very, very large. These are roughly a billion times stronger in units of G effective compared to G Fermi than the weak interactions. So that may sound unreasonable off the bat. A factor of 1 billion is a lot, but the weak interactions are weak for a reason. So the question remains whether such large self-interactions could exist in nature. And that's where we set off to try to address this problem. Now, we wanted to address this problem from a light mediator perspective. So the simplest thing, like I talked about in the previous section, is to suggest that there's a light mediator phi that couples to neutrinos via some coupling G phi. Now, in the simulations of Kreisch et al., they assumed this to be a flavor universal coupling. so that all of the different species of neutrinos delayed their free streaming until a common time. But we wanted to explore the possibility that we had off-diagonal couplings or flavor-specific couplings as well, just for completeness. So you can calculate what the effective 4 Fermi interaction strength is in this scenario. G effective goes like G phi squared over M phi squared. And in order for this to solve, or so if this is the case, then we get a G effective on the order of 10 MeV to the minus 2 if G is 10 to the minus 1 and M phi is 1 MeV. Now, I mentioned that the simulations of this this Kreische et al. Paper assumed flavor universality, and they also assumed that this interaction remained a 4 Fermi interaction for all temperatures relevant for CMB formation. Now, people commonly assume that the CMB is formed at 1 electron volt. However, the higher multipoles are being formed at larger temperatures. So it's really a broad range of temperatures over which the CMB forms. So if you really want this to remain a 4 Fermi interaction for all of those temperatures, then you want this to remain G squared over M phi squared instead of G phi squared over Mandelstam T minus M phi squared. That will pick up some temperature dependence if M phi is too light. So we really want to keep M phi bigger than ballpark 100 electron volts for this solution to work. There is a paper from April of last year that explored strong self-interactions in the complementary regime where they assumed that the mediator was nearly massless. Then this interaction scales like G squared over the temperature squared. And they found that a corresponding solution to the Hubble tension does not work in that scenario. So we're interested in relatively heavy mediators, 100 eV and higher, and relatively strong self-interactions. So if we take the preferred range of G effective and translate it into the parameter space G phi versus M phi, this is the ballpark that we're imagining. So M phi going between about a KeV to be safe and a GeV, and couplings between about 10 to the minus 4 and 1. So the SI nu band, the strongly interacting neutrino solution, is given by this green band, and the moderately interacting neutrino solution is given by this blue band. And like I said, they're about an order of magnitude separated in terms of G effective. So the question is, given the current or the previous discussion that we had about laboratory constraints on couplings and mediator masses, are these solutions viable or not? So let's revisit the muon flavored couplings first. If we take all of the different muon sensitive couplings that we discussed in the first section of the talk, we can combine them into this purple region where at low masses, the constraint is dominated by the charged kaon decay search. And at high masses, the Higgs and Z decays take over. And we see that the kaon decay forces you to be below a couple of MeV in the Mi nu solution, or you know, a few tens of keV in the strongly interacting neutrino solution. You cannot be in this heavier regime and be consistent with kaon decay searches. So then what about electron flavored couplings? Again, combining all of our knowledge from the previous discussion, charged kaon decays and neutrinoless double beta decay searches, we can effectively rule out the entire region of parameter space allowed by the strongly interacting and moderately interacting neutrino solutions to the Hubble tension. It is severely constrained if you just let phi talk to electron neutrinos. So now to really complete the picture for the muon and tau couplings, we need to take into account a little bit more information. All of the existing constraints I've discussed so far have been laboratory-based constraints, things like meson decays and double beta decay. But there's one more cosmological constraint that we need to take into account, and that is Big Bang nucleosynthesis. That shouldn't be there yet, I apologize. So now we've added a new light scalar that's order MeV in mass that talks to neutrinos with a relatively strong coupling, to the point where in the early universe, the forward and backward process of phi to two neutrinos and vice versa, two neutrinos to phi, is very much in thermal equilibrium before BBN temperatures, as long as the coupling that you're considering is bigger than about 10 to the minus 10 if phi's mass is an MeV. So this means that if phi is an MeV or heavier, we are very likely to thermalize this particle. And depending on its mass, it will only be able to decay into neutrinos and drop out of thermal equilibrium if it's significantly heavier than an MeV. If it's an MeV or lighter, then it is very likely to remain relativistic and in thermal equilibrium around the time of BBN. Now, people have done significant work in calculating how additional radiation, additional relativistic radiation, contributes to BBN. And it looks like this. In terms of the initial element abundances of helium-4, the observed abundance is shown in this green band. As a function of delta N effective, the additional contributions beyond 3 to the number of effective relativistic degrees of freedom at the time of CMB. Now, if you perform the calculation, if phi is a real scalar, it contributes 0.6 degrees of freedom, and it would predict a helium abundance that's significantly higher than the observed one. So if phi is completely in thermal equilibrium, this is bad news for BBN. So we want to avoid this. If phi is a complex scalar, which is a possibility in what we're considering, it would contribute a whole degree of freedom, which is even in more tension with the observed helium abundances. So if we go back to our muon coupled scenario and we ask, what does BBN have to say about that? We get this result. The purple line is what I showed before, this K-on decay limit. And now we have added in the BBN constraints for a real scalar in the red shaded region and complex scalar in the dashed lines. The two different red solid lines have to do with some of the specific parameters from the CMB fit that also play into BBN. Likewise for this pair of dashed lines. But we see that the strongly interacting neutrino solution is completely ruled out for the muon coupled channel. There's nowhere in this parameter space that is consistent with BBN and lab constraints. And this is the one that we really wanted to work for the Hubble tension solution. There might be a little bit of parameter space allowed for the moderately interacting solution, but it's not too promising, unfortunately. So I've talked about electron flavored constraints and muon flavored constraints. Finally, let's talk about tau flavored constraints. The lab limits on tau only couplings are much less well known. There's a limit from a tau decay search that gives you a limit on the order of 0.3 in this coupling. So there's a tiny little bit of parameter space after you take into account BBN that's allowed for the strongly interacting neutrino solution, and a bit more of the moderately interacting solution is still okay for real scalar phi. So tau neutrino only couplings could work. However, like I said a few times, the original CMB analysis assumed flavor universal couplings. So if you only had a tau neutrino coupling, you would expect that the free streaming of the nu E and nu mu bath would look different from the nu tau bath, and this has yet to be seen. So this motivates some future work from the CMB simulation side. Let me summarize the Hubble tension by showing one more figure. This is the case that truly maps on to the study by Kreische et al., where you assume a universal coupling. And we see that lab constraints in gray on their own pretty much rule out the entire allowed parameter space of SI and MI nu. And BBN does powerful work as well. I will mention that you could have a possible workaround to still have this solution be viable by having a new mediator mediate interactions among sterile neutrinos that mix with the standard model neutrinos that allows you to avoid thermalization and have large interactions around the time of CMB. But it's very difficult to get these things to align. And I'll point you to a couple of papers from March and April of this year for some interesting examples. They are worth talking about, but unfortunately, I don't have the time to delve into them any deeper. So that's all I wanted to say about the Hubble tension. Are there any questions on this before I move on? Okay, great. So I'll move on to the last section of my talk, which has to do with self-interactions and sterile neutrino dark matter. Now, we already have 3 neutrinos that we know and love, so why bother adding additional sterile neutrinos to the fray if we don't have to? Well, the first reason I think is particularly interesting from a theoretical point of view, and that is that the standard model neutrinos have masses, and in order to accommodate that in the standard model, we need to add either new particles, new degrees of freedom, and or new interactions among the light neutrinos. It's a fact of nature. Also, several experimental anomalies in oscillation experiments point towards a new neutrino with a mass around an electron volt that mixes with the light ones. Whether or not that is truly there has yet to be seen, but it's still an interesting hint. If you had heavier sterile neutrinos, maybe TeV scale, they could be connected to the baryonic symmetry of the universe via leptogenesis. And last but not least, there are hints of a sterile neutrino with a mass around 7 keV from searches for X-rays for the neutrino decaying into an X-ray and a light neutrino. So I like using these 3 examples because they really show the wide range of possible and interesting sterile neutrino mass scales. It could be as low as an electron volt and lead to things like oscillations. It could be as heavy as TeV or above and be related to leptogenesis or be searched for at colliders. And it could be kind of in the middle and be interesting for dark matter searches. So a while ago, an interesting mechanism was introduced for sterile neutrinos to allow them to serve as dark matter without running afoul of other searches for things like, measurements for things like Big Bang nucleosynthesis. If we had a new sterile neutrino at order keV mass, you wouldn't want it to be in thermal equilibrium with the standard model fermions around the time of BBN, otherwise it would modify things as we saw in the previous section. So this can be attained via freeze-in at later times via neutrino scattering off things like electrons, where mixing between the neutrino and the sterile neutrino allows you to populate the sterile neutrino bath at late times. This will lead to a non-thermal population of the sterile neutrinos, but it can give you enough sterile neutrinos such that you explain all of the dark matter in the universe. So to calculate the thermally averaged rate of which you convert neutrinos into sterile neutrinos, there are a few ingredients that need to go in. This is averaged over a mean free path of alpha, or nu alpha converting to nu s. It depends on the mass scale of the sterile neutrino. This m squared over 2e is common to neutrino oscillation experiments. Theta is the mixing angle between the light neutrino and the sterile neutrino, assumed to be small so that we didn't thermalize it in the early universe. There is an effect of quantum Zeno damping that damps this conversion rate. But the most interesting piece in my mind is this matter potential piece. Depends on the cosine of the mixing angle, which is going to be large if the angle is small, and the matter potential, which is generated via the interactions involved in the process. Like I said, we need small mixing to avoid thermalization in the early universe. So really, it's important to generate the mixing at late times and a large effective mixing at late times via this matter potential. And that's generated via loop diagrams like this, where you have a neutrino coming in and a W or Z loop with the electron or the neutrino closed into a neutrino, or these little fermion tadpole type diagrams connected via a Z boson. So you can perform this calculation as a function of the sterile neutrino mass and the vacuum mixing angle, and you can determine for what values of the parameters do you bring this process into thermal equilibrium late, and do you populate enough sterile neutrinos to account for all of the dark matter in the universe. Now I mentioned that there's also a hint for a order keV mass sterile neutrino from X-ray searches. So we can ask, is the Dodelson-Widgerow mechanism consistent with that excess? And I chopped off the label on the x-axis. I apologize. This is the sterile neutrino mass in keV here, and the vacuum mixing angle given as sine squared of 2 theta on the y-axis. There is a line here shown that is where this Dodelson-Widgerow mechanism can account for all of the dark matter in the universe, compared against the data that's seen in the X-ray searches as the red dot with the error bar. And we see that it's significantly lower than the Dodelson-Widgerow prediction, and it's in tension with some other X-ray searches. So if this hint turns out to be true new physics, then we're going to need some additional ingredients to understand how these neutrinos were thermalized in the early universe beyond the standard Dodelson-Widgerow mechanism. So the short answer is that no, this excess is not consistent with the standard Dodelson-Widgerow mechanism. However, you can effectively move the Dodelson-Widgerow line by introducing a finite lepton number asymmetry in the early universe. This modifies the matter potential in the previous slide, although it's hard to constrain that scenario. So the question is, what are some other ways to move the Dodelson-Widgerow mechanism line beyond using lepton number asymmetry? And the answer, which you shouldn't be surprised given the theme of this talk, is strong self-interactions. So what happens if you add strong self-interactions beyond the weak interactions to the picture of converting into sterile neutrinos across temperature scales? And the answer is that it's very interesting in my mind. So if you have neutrino self-interactions, you can have this type of S-channel diagram in the early universe where two of your light neutrinos come in, annihilate into a phi, and decay back into a neutrino pair. But if there's large enough mixing, you can populate the sterile neutrino state in the final state. Now, if phi is very heavy compared to the temperatures that you're considering, this will look like a 4 Fermi interaction, similar to the standard model interactions that were considered in the Dodelson-Widgerow case. However, if phi is at or below the temperature scale you're considering, you can populate the phi and have it decay into neutrinos and sterile neutrinos via the process shown in bottom right. So this is going to give us very different phenomenology depending on the mediator mass we consider. And so to show some numerical results using this full potential on a project that full disclaimer, I was not involved on this. This was from Andre, Manabrata, Walter, and Yue back in October of last year. They calculated for parameters consistent with the 7.1 keV sterile neutrino excess, the allowed region of parameter space for the mediator phi and the coupling to the active neutrinos lambda, for which you populate all of the dark matter being this sterile neutrino. And there's some interesting regimes going on. in general, no matter what you pick for the sterile neutrino mass and mixing, you get these so-called S-shaped curves. If you are in this A region where phi is relatively heavy, it really looks a lot like the standard Donaldson-Widrow mechanism, just with a new effective G Fermi scale involved. Down in area C, however, you're dominated by this direct production via your mediator. So the scaling works out to be a little bit different in powers of masses and lambda down here. And the rich region comes in this turnaround region B, where these two processes are competing for explaining the population of the dark matter. So this allows for much more parameter space in the sterile neutrino mass versus mixing plane to be explained by this type of mechanism than just the standard Donaldson-Widrow approach. So let's take this scalar mediator case and compare it with some existing and future limits. In this work, they considered the mixing to be with muon neutrinos, and they show the predicted relic density line as a function of mediator mass and coupling versus some existing constraints, such as thermalizing phi before BBN and modifying BBN, K-on decay searches, and some searches that I was involved in using the deep underground neutrino experiment mirror detector. So the place where I came in was to ask the question, well, what about vector mediators? We found out that there could be some...
Excuse me?
Yes.
Excuse me, before you proceed, in this plot, what do you assume for the mixing angle between the sterile and the active neutrinos?
Good question. The mixing angle is assumed to be a magnitude consistent with the Donaldson-Widrow, or sorry, the 7.1 keV excess, and it's assumed to mix with only muon neutrinos. So the mixing is only with muon neutrinos, and the new mediator phi talks only to muon neutrinos.
Okay, thank you.
So that'll be the case for all of the scenarios I'm considering going forward. You could generalize this to be more flavor dependent. It just makes predicting these types of things a little more complicated. Okay, so vector mediators. If you want to add a vector that couples to neutrinos but isn't severely constrained by other searches, it's not as obvious as the scalar case. So we considered 3 separate scenarios. One with a pure neutrinophilic vector boson, and I'll explain that on the next slide. The second case we considered was where the vector boson was a gauge boson of B minus L, or a gauge boson of lepton number flavor muons minus tau, L mu minus L tau gauge boson. So the pure neutrinophilic vector case, we introduced in our Lagrangian a term that looked similar to the scalar case. So here we've taken the standard model and added in the sterile neutrino and its mass and mixing, kinetic and mass terms for this new vector, and an effective operator dimension 6 that looks kind of like L bar H dagger gamma LH V over lambda squared. And after electroweak symmetry breaking, like in the case of the scalar, this will lead to a neutrino V interaction that we can probe with many different searches, including meson decays and Higgs decay searches, etc. So I'll just show a few summary plots from this work. This is where we consider the pure neutrinophilic vector phi. So let me unpack this a little bit. All of the filled in regions are existing limits. Blue are the meson decay searches K to mu nu V and D to mu nu V. Z decay searches are in red. Existing Higgs decay search is shaded in purple, and high Lumi LHC Higgs decay search is shown in dashed purple. If you are too light in terms of the vector mass, it will thermalize before BBN and run afoul of those types of searches. Also, if the coupling is relatively low, V can be emitted during supernova formation and can deplete a bunch of the energy that would have gone into neutrinos and would be inconsistent with what we saw with supernova 1987A. Now, there are two solid lines, one black and one gray on this, that show the combination of V mass and lambda for which the relic density of the sterile neutrino is equal to the observed relic density of dark matter today for a couple of specific pairs of the sterile neutrino mass and its vacuum mixing angle. The black line is an extreme case where we go as heavy as we really can for this mechanism to work with a corresponding mixing that's allowed by astrophysical searches. And we see that this is nearly completely ruled out by existing laboratory probes and will be completely covered by future ones. The gray line is the one that's consistent with the 7 keV excess from X-rays. And we see that at high mediator masses, this is ruled out by Higgs decay searches, and future Higgs decay searches will be able to push this limit a little further, but there will still remain some viable parameter space after the next generation of experiments. However, you can't go too low in vector mass for this to work. The other models that we considered, like I said, were B minus L and L mu minus L tau, and I'll show one figure for each of those. Again, there's many things to unpack on this. I'll try to walk through it. For a B minus L gauge boson, there are many searches for direct searches from experiments like Texono, CHARM, Babar, and LHCb that constrain this gauge coupling to be bigger than about 10 to the minus 4 for many ranges of masses. If you can produce the vector boson in a beam dump search and look for its decay downstream, these purple regions constrain parameter space in this area. And the black and gray lines correspond to the same combinations of sterile neutrino mass and mixing as I showed before, where now we see that for the B minus L solution, the heavier 50 keV sterile neutrino is completely ruled out by existing data. And the 7 keV is much more in tension with existing data. It would need to be in a very narrow range of mediator mass and coupling to work. And there are a variety of future probes that are sensitive to B minus L gauge bosons, including Phaser at the LHC, LDMX, the electron scattering experiment, and Bell2 sensitivity to B minus L gauge bosons in blue. The combination of all these things will be able to definitively test this solution for a B minus L gauge boson, which I find very exciting. The last one that I'll discuss is L mu minus L tau gauge boson. Again, existing limits are shaded. Observation of trident neutrino interactions at CCFR in red. The orange is BBN constraints on this. Again, supernova production in purple. And then the preferred region as given by the relic density in gray and black. Now, there are a variety of future proposed probes that aren't as concrete as those shown in the B minus L plot, including a muon missing momentum experiment, SHIP at CERN, and a dedicated NA64 experiment that involves muon upgrades that could probe all of the 50 keV solution and much of the 7 keV solution. So future experiments could really say a lot in terms of if this is a B minus L gauge boson mediating this interaction or L mu minus L tau. But the neutrinophilic scenario is a lot tougher to constrain, which isn't too surprising given the way that we approached this. All right, so let me conclude. The self-interacting neutrino hypothesis is very interesting, and it remains largely unconstrained due to the difficulty of observations with neutrinos. More data will allow us to better understand whether they have additional interactions beyond the weak interactions. If they do have these strong interactions, then their free streaming, cosmologically speaking, can be delayed, and can have something to say about the long-standing Hubble tension. Finally, if you have these strong interactions, you could populate KeV scale sterile neutrinos to the point where you can explain all of the relic density of dark matter in the universe, consistent with current data, but testable by future experiments. Thank you very much.
Thank you. So questions? Okay, I have one question.
Sure.
So you said to satisfy the relic density, the parameter space in the parameter space there is some S-shape features.
Yep.
But why this is why the slope is very different between some 1 GB or some dramatically changed here.
You mean this
Yeah,
region?
Yes.
It has to do with the. Let me find the right diagram. It has to do with the competition of these two types of processes: the on-shell phi or V contribution to the sterile neutrino relic density versus the off-shell contribution. And these processes would interfere if M phi is around the temperature of interest. And it's the trade-off between these two types of processes around the relevant temperature. And this is this regime B.
Okay. 1G run. Okay. So, any other questions? Professor Pagilwan, please.
Yeah. Hi. I have one question about this Hubble tension ameliorated by this delayed pre-streaming.
Yeah.
Could you explain the mechanism in a simple terms? How the delayed pre-streaming can improve the Hubble tension?
Sure. So I am by no means an expert on the cosmology side of this. That's where I defer to my collaborators on this, but I'll try to my best. What happens if you have the neutrinos not yet free streaming as the CMB is forming is it induces a phase shift to the peaks of the CMB power spectrum. That free streaming, it causes a phase shift in that is similar to a phase shift that you get if you have additional relativistic degrees of freedom at the same time. And so it's kind of a combination of these types of phase shift effects that modifies how you extract the Hubble constant from the CMB power spectrum and from measurements of the sound horizon at the time of CMB. So it has to do with several things all at once. It has to do with the fact that the CMB measurement of the Hubble constant isn't really a measurement, but an extracted parameter from many things interacting. And it has to do with this delicate balance of the delayed free streaming giving this phase shift and this additional N effective at the time of CMB. I mentioned that in order for this solution to work, you need large N effective, and it's this interplay between the free streaming and N effective that leads to it working.
Okay, so basically it is kind of affecting the sound horizon.
Exactly.
Okay, thank you.
Of course, thank you.
So, any other question? Okay, I think there is no more questions.
Okay.
Thank you very much for your talk.
Yeah, thank you again for the invitation. This was a real pleasure.
Yeah. So, yeah. Oh, yeah, please.
Thank you very much.
You're very welcome.
So, we'll have some discussion session after 10-minute break, or is it
Sure.
okay? Okay.
Yeah.
Then we will have some discussion session after 10-minute break.
Okay, great.
Okay.
Should I just stay on the Zoom call?
Oh, yeah, sure.
Okay, will do.
We will resume at 11:16.
Okay.
Okay. Thank you very much.